It's a big pleasure for me to introduce our next speaker, Charles Batty from the University of Oxford. So his title is Rates of Decay of Energy via Operator Semigroups. Charles, we're looking forward to your talk.
Well, thank you. So when I registered for this conference 2 or 3 months ago, I didn't volunteer to give a talk. There were various reasons behind that, but one of them was that I wasn't sure what I should talk about, whether I should talk about this topic, which is now in a rather complete state and has gone quiet for the last couple of years, or whether I should talk about what I've recently been doing, say, over the last 3 years, which has been work on functional calculus and have a more abstract feel to it than what I'm actually going to talk about. But if you want to hear me talking about functional calculus, I will be one of the main speakers in the IWOTA meeting based in Lancaster in England in August. There are 2 IWOTA meetings, one in the United States and one in England this year because the one in Lancaster was postponed from last year. Anyhow, the topic that I'm going to talk about has to do with rate of decay of energy. That's where it gets many applications of, well, various systems, but a fairly typical one is a damped wave equation of this form, where the term involving a function a of x represents the damping, and that has to have a certain sign, which is a is non-negative. This is not the only possible form of damping. This is damping taking place on the interior of a bounded domain. One could also have damping coming from the boundary conditions, but I'm just showing you this. The A is damping, but it can be 0 on parts of the domain omega, and elsewhere it should be positive. And then there are various regularity conditions that you might need. A smooth boundary perhaps, and A being continuous, although those things are not necessarily essential. Then the energy of a wave can be represented by this integral and the function E, U, and T, where T is the represents time, roughly speaking, and U is the nature of the wave at the time. Now, this topic of energy decay and rates has been active for quite some time, and various things were established by, say, the 1990s, leaving out certain degenerate cases. The energy will tend to 0. If the domain of damping in the form of the wave equation that I showed you before, that's the area where A of x is positive. If that satisfies a certain geometrical condition, then it was shown in 1992 that the decay occurs at an exponential rate. And so that deals with cases where the damping is on, in some sense, a large part of the domain. In other cases where the geometric optics condition is not satisfied, there began to appear results showing that decay occurs at a polynomial rate or a logarithmic rate, uniformly for smooth initial data. So smooth here means initial data which is at least once differentiable or something like that. Now, we can reformulate this problem in operator theory, where we take X to be the first order Sobolev space across L2 of omega. So this is a Hilbert space. This is not surprising because energy is given by squares, and in the formula for the energy, we had squares on the integrands. The operator A is given in this form, where A of x means multiplication by that function A, and with this domain. And then if we put u of t equal to little u of t and du by dt in x, and here's the energy is now expressed in terms of the square of the norm of that Hilbert space, and the damped wave equation corresponds to this Cauchy problem. U prime of t is equal to a u of t, and u of 0 is something or other, two initial data points. And this then is the first order Cauchy problem that corresponds, roughly speaking, to operator semigroups. Now, in 1996, Lebeau established that, for the example that I've described, that the spectrum of A is contained in the open left half plane. So there are no points on the imaginary axis which are in the spectrum of A. And he also showed that the resolvent function on the imaginary axis, S is a real variable here, that the norm of the resolvent grows at most exponentially as S goes off to infinity, either upwards or downwards. Now, the result I mentioned before, that the decay is at least logarithmic, actually corresponds, as you will see later, to this resolvent growing at most exponentially. And Lebeau showed that A generates C0 semigroup of contractions, TT, that's the operator A in the matrix form that I showed you. And so in particular, the resolvent of A is the Laplace transform of the semigroup. When you consider this Laplace transform, you have to interpret it in the strong operator topology, because the semigroup isn't strongly measurable relative to the operator norm. So strictly speaking, I should put in some initial data on both sides, but that typically gets left out. And then the evolution of the energy is given by applying the semigroup to the initial data. So then estimates started to be obtained by certain groups of people in a fairly uniform way, using this operator setup and using semigroups. And the estimate that comes out of this are uniform for initial data which are in the domain of A. So that means that they're estimates for the norm of the semigroup with the resolvent in here. It doesn't matter which lambda in the resolvent set you choose, because if you change lambda, you only change this norm by at most some constant factor, a multiplicative constant, so you're not really changing the rate of decay. So multiplicative constants here, I'm more or less going to ignore them in this talk, because I regard the rate of decay as being a class of functions with a similar rates. So Lebeau, in his paper, having established these things about generating a semigroup of contractions, he went on then to formulate some theorem about semigroup of contractions on Hilbert space, from which he was able to extract information about norm TT, A inverse, say, from information about, well, in fact, the growth of IS minus A to minus 1. And the estimate he got wasn't quite the best he could possibly have got, as it's subsequently turned out. But he showed the decay was at least almost logarithmic. Then Nicola Burke, who was a student of Lebow, improved that result to show that in that case, the rate of decay was at least logarithmic. Then there were various other people involved. There's a well-known paper by Liu and Rao about what happens in rectangles, which I might come back to later. And other people who were specifically interested in decay of energy of damped waves and similar models. But they were writing papers where they set this up with the operator form, use the PDE to get information about the norm of the resolvent, and then they produce their own results, general results for contraction semigroups on Hilbert spaces of the same form that Lebow did, and produce various answers. None of these answers, apart from the one by Burke, none of these answers turned out to be as sharp as they could be in the end. There was another rather different paper by 4 people, Batty, Engel, Proust, and Schnabel. This was an abstract paper. It was set in the context of Banach spaces, not just of Hilbert spaces, and it was looking at polynomial rates. And they showed something similar. They assumed a polynomial rate of growth of the resolvent on the imaginary axis, and got out a polynomial rate of decay for TT A inverse. But actually, their polynomial rate of decay wasn't quite optimal either. But they were fairly close, these people, as it turns out. Now, that's sort of what was going on in the 1990s and just into the 2000s. But let's go back another 60 or 70 years to a theorem shown here. This is not quite the most general formulation of it, but it'll do for our purposes. This theorem was found independently by Ingham and Karamata around about 1933 to 35. Neither of these people was interested in decay of energy of waves. Ingham was basically, he was part of the Hardy-Littlewood school in Cambridge. In particular, he was associated with Littlewood. And Karamata, who was a Serb, was in Belgrade at this time and later in Geneva. And he was interested in analysis as its own right and functions and so on. They were almost exact contemporaries, born at the very beginning of the 20th century, and they died within a few weeks of each other in the later 1960s. They didn't formulate this results for Banach space valued functions. They just formulated it for scalar functions, but there wasn't really any difference. So they considered bounded measurable functions on R+, so you can take the Laplace transform for the real part of lambda positive, strictly positive, and then it's quite likely that the Laplace transform will extend analytically at some points on the imaginary axis, but let's assume that it extends analytically at each point on the imaginary axis. Then they got that if you take the integral, the primitive of the function f, the integral from 0 to t, and let t tend to infinity, that gives you f hat of 0, where f hat is the extended value at the origin. Now, the proofs of both Ingham and Karamata were not the proofs that I'm showing you here. Ingham and Karamata used more like Fourier analysis methods. And this is a proof via, well, contour integrals. This proof dates from 1970s and 80s by Newman and Korovar, both of whom were interested in finding things which would help to provide elementary proofs of prime number theorem, rather like Ingham. And indeed, this was quite successful. So this version of it was Korovar's version, which was, he actually appeared in the Mathematical Intelligenza. And the proof is really quite very simple. So here's a diagram. On the left is a shaded region. That's where f hat does not extend to. So f hat is an analytic holomorphic function on the right half plane, on and across the imaginary axis, and a bit further, so on. So we're going to take a contour integral around this contour gamma, which is the semicircle in the right half plane of radius r, and then some path in the left half plane, which comes back and joins up the ends and stays inside the region where f hat is holomorphic. So you can then take this integrand, and this has a singularity at z equals 0. So the value of this is just what you get by putting the rest of it equal to z equals to 0 in that, and that gives you this quantity here. So all we need to do is to estimate this contour integral. Let's first estimate it over the right-hand semicircle. And here we have a factor 1 plus z squared over r squared, which vanishes at the points IR and minus IR, which otherwise would have been problematic if we didn't have control of f hat in that region. But when we look at this term, one can estimate this, and this turns out to be not too much big, and it's compensated by this term here near the points IR. So estimating the right-hand semicircle gives you the infinity norm of f divided by r. Now for the left-hand semicircle, we split this up into two integrals. One is the 1 plus z squared over r squared times this other integral. And that one we can deal with easily because this other integral is an entire function. So we can replace the left-hand part of our contour by the left-hand semicircle of the circle of radius r. And then we can estimate that in a very similar way to the one we did on the right-hand side. And that gives you another term, the infinity norm of f divided by r. And the other bit that we're left with consists of the integral along this part in the left half plane of 1 plus z squared over r squared, f hat of z, e to the tz, dz over z. Now, having got this estimate, you just let t go to infinity in here, in this term, and because you've got e to the tz and the real part of z is negative, this integral tends to 0. So then we get that the lim sup of this difference as t goes to infinity is less than twice norm f over r. And then let r go to infinity. And then this tells you the limit of this is 0. So that gives us the result. Now, when we pass to a semigroup version, so, well, it's going to be standard that A is the generator of a C0 semigroup on some Banach space X. Then the result says, it tells you, in fact, if you look carefully at it, that if this semigroup is bounded, and if the spectrum of A does not intersect the imaginary axis, so that means the spectrum of A is contained in the open left half plane, then you get the limit of the norm TT of A inverse in operator norm is 0. Now, you might think that I had to put in the vectors X again, but actually one does do that, but actually the estimate that comes out is uniform for norm X less than or equal to 1. So you get the operator norm out of it. Then I should just remark, as this is rather an aside, that this theorem has to do with work that Wolfgang Arendt and I were doing at the time, and this has the consequence very easily that the limit of TT of X is equal to 0 for all X's in X, because the domain of A is dense and the semigroup is bounded. What Wolfgang and I went on to do was to look at weaker assumptions than this set being empty, which still gave this conclusion for convergence of TT in the strong operator topology. There was a long story behind that work. It became quite a famous theorem very rapidly. But anyhow, I'm not going in that direction. But one of the things that we noticed at some point was that you actually got operator norm convergence out of our proof. Our proof is a rather crazy proof. Nobody believed that it was a good way to prove the more general results, but our proof, it actually was a good way to get this operator norm coming out. Now, time passed, and one of the things I was conscious of was that our method would provide a rate of decay for TT A inverse, norm of that operator. But I never actually worked out what the rate was that came out of this. But in the year 2008, I received a paper from Thomas Deukertz, who was a student of Nicola Burke, who was a LeBeau's student, which contained this theorem that I show you here. This is as you can see, this is the Laplace transform version rather than the semigroup version. And so assume that f hat extends analytically to a region in the left-hand side where the real part of lambda is greater than 1 over m of the imaginary part of lambda. And assume that f hat of lambda is less than m of the imaginary part of lambda in that region. Actually, you might not want to take the same m here. Whoops. I'm using M to define the region, and I'm also using it to define the growth of F hat. You might want to separate these out into two different M's, but for the semigroup purposes, basically it's natural to take the same M here. And if you do separate them out, you find that actually the shape of the region is much more important than the growth bound. Anyhow, one then obtains an estimate. Well, this was what was in Duykert's paper. One obtains this estimate for this difference, f hat of 0 minus the primitive of f, less than big constant c, but multiplicative constant, divided by the inverse function of m log at the point c of t, where c is some number between 0 and 1, strictly between, and m log is the function m slightly increased by multiplying by basically log of m or log of s, whichever is bigger, or the sum of the two. Now, the semigroup version of that one supposes we have a bounded semigroup. I haven't written that in again here, but it is still assumed to be a bounded semigroup with no spectrum on the imaginary axis. But we assume that the resolvent, the growth of the resolvent is bounded by m of s, or for simplicity, we take m of the absolute value of s. Then it's automatic by Neumann series expansion for the resolvent. A similar estimate is obtained, perhaps with a 2 factor in here, in a region of which extends to the left 1 over twice m. And from that, you can get that for certain values of c, the norm of TTA inverse is big O of 1 over m log inverse of CT, where m log is as before. Now, this result was already better than any of the results on Hilbert spaces. This result was on Banach spaces. It was better than any of the results on Hilbert spaces, except when m grows exponentially. But our result was valid in Banach spaces. I'll show you later on in a short while, perhaps, what the difference between m log and m log m itself makes here. But we also have in our paper a sort of converse of the result that I've just described. So assume now that we have TT with some resolvent in. I'm not assuming that A is invertible at the moment, so I have to change lambda here to be equal to 1. So assume TT, norm of TT resolvent is less than some function m, which is decreasing to 0. Then it follows that there is no imaginary spectrum and no spectrum of A on the imaginary axis. And furthermore, the norm of the resolvent grows at most like n inverse of some small constant now over S. This result, roughly speaking, it tells you that in this result, you can't do better than getting 1 over m inverse of CT, because you can just choose the m. Well, I required the m to be an increasing function and to be continuous, but you can then just take m to be, there's a particular definition of that works. So this would suggest that the optimal rate of decay in the Ingham-Karamata theorem would not be 1 over m log inverse, but 1 over m inverse, or constant over these. And then the question was, can one achieve this? Anyhow, we didn't put a great deal of effort into trying to achieve that. We wrote up a fairly short paper on it. Oh, I got involved because Decay's proof was also used very complicated methods. But I knew how to do the Ingham-Karamata theorem, how to get from once one had got the resolvent estimates for the operator A, how to get the estimates for TTA inverse. I knew how to do that, and so we put in the much shorter proof that I explained to you before.
Okay.
Now,
so can we start? Yes, good. Yes, we can start. So let us share. Sharing is caring.
Right. Can I? So I just want to go back to cover another very special case, which in a sense had already been covered.
Jacku, chciałeś wykład Charlesa.
So these are well-known results to anybody who worked in semigroup theory, particularly the Gerhard-Preuss theorem, which is the second one.
Okay. So let us continue with our sort of like refresher
Please
course
switch off your microphone.
on linear systems. Okay. So, as I said earlier, if we are lucky enough to have
I'm sorry,
eigenvalues and eigenvectors for
right, I think they've stopped. So I just remind you, you may not know the Weiss-Vrobel theorem, which came from the 1990s. This is on Banach spaces. If A generates a C0 semigroup and the resolvent is bounded in the right half plane, then TTA inverse decays exponentially. And the Gerhard-Preuss theorem says you can do better than that on Hilbert spaces. If the resolvent is bounded on the right half plane and X is a Hilbert space, then actually the norm of TT decays exponentially. So if you take M of S to be the constant function C, then the M log theorem does actually give you decay at this exponential rate for TTA inverse. But these two results, in a sense, don't quite fall into the category of the results that I'm talking about in this talk. These results don't, in fact, depend on T being bounded, whereas everything else in this talk does depend on the semigroup being bounded. Here I've showed a rough table of what's happening for certain functions M of S, and then what are the functions 1 over M inverse and 1 over M log inverse. So if M of S is just constant, well, M inverse doesn't really exist, and this quantity turns out to be, well, a multiplicative constant times e to the minus ct.
I'm sorry, Charles, I see only formulas but no text. Is it correct?
There's no text.
Ah, okay.
This is just a table.
Okay.
I didn't put in a load of lines. I'm sorry, I didn't get around to doing that. So here are 4 possible functions M of S. This is constant, there's logarithmic growth, there's polynomial growth, and there's exponential growth. And then here you see the form of 1 over M inverse of CT ignoring a multiplicative constant. And then 1 over m log inverse of CT. So the first row here was, as I just described on the previous slide. Let's go to the bottom row. If m of s grows exponentially, then in fact, you get the same answer for m inverse and m log inverse, up to a multiplicative constant. You get 1 over log t. And that's what Nicola Burke got. In between, we have two other cases, logarithmic growth of m and polynomial growth of m. And one that received the most attention immediately was the polynomial growth. The logarithmic growth, I'll come back to it at the end of the talk, I hope. So as you see, the difference between the two rates is itself the power of the logarithm, which is present over here, but not present over here. So anyhow, we wrote up the paper, and in the paper we mentioned that we thought, we wondered whether the 1 over m log inverse could be improved in Banach spaces. We thought it quite likely it could not be improved always to being 1 over m inverse. But we also said that it might be easier to improve it on Hilbert spaces. And then very, very quickly after we'd written up the paper, Alexander Borochev and Yuri Tomilov got into this, and they came up with two answers to those questions. M is growing polynomially. And in that case, if we're talking about scalar functions, as in the Ingham-Karamata theorem, or about semigroups on Banach spaces, it's not possible to improve the conclusion of the M-log theorem. No slower rate here, no faster rate here works for every such function, for every such Laplace transform. But in the Hilbert space case, if we have a m equal to this, we have this estimate on the resolvent, then one does get the 1 over m log, 1 over m inverse result coming out in Hilbert space. This proof was actually quite short and easy compared with what they did in this first one. So now if I just go back to the previous slide for a moment, that's saying that in the polynomial case, this is the right answer on Hilbert spaces. This is the best answer that you could get that works for all semigroups on Banach spaces. Then slightly later, it says 2016, that was the date of publication, but most of the work on this was done by myself and Ralph Schill and Yuri Tomilov starting in 2012. The paper was accepted in 2013, but didn't get officially published until 2016. And we considered cases where m is roughly polynomial, like s to the alpha. I'm not writing 1 plus s to the alpha now, and just think of s as being fairly large. But adapted by something like a power of log s. This is a negative power of log s. And here's another thing that's a bit... Then we were able to improve the result on Hilbert spaces to 1 over m inverse. If we had m slightly bigger than s to the alpha, we were not quite so successful. We couldn't get the optimal result, as we thought, but we could get closer than the m log inverse did. We also, in this paper, looked at the case of semigroups of normal operators on Hilbert space, which we can deal with quite easily because they have the property that the spectral radius is the same as the norm. And we found that then we only got the M inverse theorem working, the stronger result working, if and only if M is a function of what is known as a function of positive increase. I'll define that later in the talk. I hope I will have enough time for that. So we already knew at this stage that some functions would not work even if they were growing not particularly fast. Now, subsequently, things have moved on there, and a generation of slightly younger mathematicians than some of us, Jan Roosendaal, David Seifert, who I think is in the audience for this talk, and Reinhard Stahn, showed this result, published in 2019, bounded semigroup on Hilbert space, IS minus A, bounded by M, where M is increasing and satisfies this property here, which is actually a possible definition of M being a function of positive increase. Then norm TTA inverse is big O of 1 over M inverse of T. So what are the functions of positive increase? Here are 4 equivalent characterizations of that property. This is the one I showed on the previous slide. It's the one we found in our paper, I think. Here's a different one, which looks a bit surprising that this is the same as the previous one, but it is. They are the same. They are equivalent to each other. And then there's a log coming in. Here's another reformulation. And then here's a description in terms of the inverse function of M. And what this last one tells you is that the asymptotic behavior of the inverse function of M does not depend on this constant C. So that's why in this result and the one before, I did not put a C in here because the up to big O, they would be the same function. So what functions are not functions of positive increase? Well, what increasing continuous functions are not of positive increase? This is easier to say perhaps than what functions are of positive increase. There are 2 ways a function can fail to be of positive increase. One is if the function does not increase, well, if the function increases slower than polynomially. And the other possibility is that the function has very irregular periods of increase. So it increases very fast for a time, then increases hardly at all for a very, very long time. Then it increases very, 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 very fast, and so on. So overall, such a function could increase fast, but not be a positive increase because it's too irregular. So, well, perhaps I should say that for that theorem, back here, RSS theorem, as I sometimes call it. They did not use the sort of methods that we used. They went back to using Fourier analysis methods and doing very careful estimates. But they did use some things that could be recognized as being connected to our proof. They were introducing certain functions which played the role of 1 plus z squared over r squared in our proof, for example. Now, there have been some other results coming out more recently in the last, well, in the last decade, say. So one is about the case of slow resolvent growth, logarithmic growth of the resolvent. Then Burke and Christensen came up with an example on Hilbert space. This isn't a genuine example of coming from a physical system and sound waves and so on, where m grows logarithmically, but the norm of TTA inverse is like e to the minus c to the half. Now, if we just look again at my chart, that was the bound at this end. So for log s, even if you're on Hilbert space, you can get this coming out. But you can also get this one coming out. So it's not clear if you've got logarithmic growth of the resolvent on Hilbert space, it's not clear what else determines whether the growth of TTA of inverse is like e to the minus t or e to the minus t to the half or something in between. Whereas for the polynomial case, we now know that if you're on Hilbert space, the growth must be t to the minus 1 over alpha. If you're on Banach space, this is the best you can do. I just go back. One can consider a case when you have one point, say the origin on the imaginary axis, which is in the spectrum. You then throw in an extra assumption that the resolvent near the origin and on the imaginary axis has some, whoops, should this just say increasing? No, I think decreasing is all right, yeah. And then you can get rates of decay for the norm of a 1 minus a to the minus 2. This a is necessary here to make things not blow up at 0. And this is, various versions of this have appeared recently, including in the RSS paper. There are also results for discrete semigroups where T is power bounded and the spectrum of T has just one point on the unit circle, take it to be 1. You can then get rates of decay for T to the n identity minus T. The fact that this goes to naught is the Katznelson-Safreri theorem from the 1980s. And then it's been developed into a rate by 2 of my former students now, David Seifert and Abraham Ung. Right, okay, have I finished? I think I've probably finished. Oh no, not quite. There are 2 further questions. Can all regularly varying rates be achieved? Well, we have a result going in that direction, again, due to partly to Rosendahl, Seifert, Stan in their paper, but also a very similar example in the paper of Benaisa and Reifer. And this again comes from a model of sound propagation. So they showed that at least for the index, that's the value of alpha in the regularly varying functions, that's the functions of the form s to the alpha times something that's hardly varying. they can all be achieved. So it's probable that there are examples without this constraint on the index. The other question, which is still completely open, I think, is what about LP spaces where P is not equal to 2? Now, in this type of topic before, it's usually turned out that if you've got a result that works in L2 and works in Banach spaces, you get some sort of form of interpolation between. So one might expect or guess that norm of TTA inverse when you're on an LP space for P not equal to 2 is given by something with some power of a logarithm in it. So for P equals 2, alpha 2 would be 0, whereas for P equals 1, alpha 1 would be 1, according to our previous results. But is there a continuous function alpha P of P which interpolates between those two results? That remains open. I know that RSNS tried hard to prove this, and so far as I'm aware, they haven't succeeded. And I'm not sure that anybody is trying nowadays. So that's where things end. Thank you.
Wolfgang, your microphone is off.
Charles, many thanks for this very beautiful, enlightening talk. Other questions, comments, remarks?
I have a comment and a question. First of all, that's really enlightening, and I will be happy if you contribute some of those problems with the context to our list of open problems. That's really the things which should be included to courses on semigroups, and I will include maybe some of this in my introductory level course on semigroups that I give in Nizhny Novgorod. Thank you. That's really very nice to see and to
yes. Well, well, subject to discussion with David Seifert, because the question really comes from him and his collaborators. I'm thinking of putting this open problem about LP spaces in your list.
Yes, of course, the person who inserts the problem in the list may not be the author. It's okay. You just point out who is the author.
Well, so, if David's strongly opposed to it, in order to
that would be wonderful.
Terms with him.
That would be wonderful. Please, everyone, join in. And my question is the following: you are posing some conditions on the spectrum, but what will happen if you ask about the parts of the spectrum? There are many ways to divide spectrum into parts, and maybe this can have some impact on the things which you discuss.
Not, I think, on this, what I talked about here, except for the bit about where I talked very briefly about convergence to zero in the strong operator topology. There is a distinction in the spectrum because one needs to make an assumption that no points on the imaginary axis. Well, the assumptions there are typically that the part of the spectrum on the imaginary axis is a countable set, and none of those points is an eigenvalue of the adjoint operator.
So generally, it's not important. Is it continuous spectrum or residual or essential? So it's not just the spectrum, and that's all.
Yes, yeah.
Thank you very much. That's very interesting, really enlightening.
Yeah, thank you. Are there further questions, comments? Charles, I was puzzled. You, well, in the first third of the talk, you said the domain of analyticity is more important than the bound.
Yes.
Could you say what you mean by that?
I may get this slightly wrong, and David may correct me. He's had more to do with that than I have. But roughly speaking, if I remember rightly, so you've got M here and K here.
Yeah.
Now, if this becomes K, then I think the K appears in the logarithm term. It's something like that.
Yeah. Okay. Yeah. Thank you. And may I add, now coming back to the waves, I mean, why are these people so much interested in these estimates? I mean, say on Hilbert space, you have this estimate on the resolvent, and then you get the energy. Can one explain this, or is this?
I don't know. I'm the wrong person to ask.
So I mean, or maybe the estimate on the resolvent, it depends just on the little a, is that right? I mean, just on the damping. So
no, it depends on the shape of the domain as well.
Okay. Yeah. I understand.
Yeah.
Of the domain on which you look for the wave equation. Yeah.
Yes.
Yeah. Okay.
So corners are bad things in a sense. So the result of Liu and Rao dealt with a rectangle where you had damping, say in the right half of the rectangle and no damping in the left half. And then the geometric optics condition is not satisfied. And the corners were potentially troublesome. So that was one problem, but it perhaps depends even more on the geometrical property. So, I mean, we know that the geometrical property discriminates between exponential and lesser than that.
Geometrical properties of omega of the domain, or
yes.
Okay. Okay.
So the rectangle has two opposite sides, and if you take rays, bounce it backwards and forwards vertically in the part where there's no damping, that's why the geometric optics condition isn't satisfied.
Okay. Are there other comments, questions? Well, then, Charles, we thank you again for the wonderful talk. And we will continue in 2 minutes. Well, we have 2 minutes. Richard, may I ask you, did we meet in Warsaw in '83? Yeah, or you don't have your microphone, maybe.
Richard, your microphone is off. We do not hear you.
My microphone is off.
Now it's okay. Yes, we probably met at this time. Yeah.
Yeah, in 1983, I remember.
Well.
Yeah, in Warsaw. And yeah.
I should share my screen, yes. A moment.